Hi friends, welcome to our YouTube channel Naraj Academy. In this lecture, we are going to discuss the 10 more questions of the AP Transcode 2019 solutions in a very detailed manner. If you like the content of our channel, then please do like, share and subscribe our YouTube channel and don't forget to press the bell icon button. So whenever we upload a new video, the direct notification comes on mobile. If any improvement is needed in your video lectures, then please do comment in the comment section. We will definitely include all those information in the coming lectures. So why do we waste more time? So let's get started. So now we are going to solve the 41 question. See the question here. Which bridge is best suited for the use in harmonic distortion analyzer? So what is the bridge which is best suited for the use in harmonic distortion analyzer? Option A, Heaviside bridge. Option B, Kelvin double bridge. Option C, Wien's bridge. And option D, Shearing bridge. So out of the four options, option C, Wien bridge is the correct solution of this question. So Wien bridge is best suited for the use in the harmonic distortion analyzer. So let's discuss something more facts of this one. So now we are going to discuss some facts of the Wien's bridge. So Wien bridge is used for the measurement of the unknown frequency in a given circuit. It is used for the measurement of the unknown frequency in a given circuit. So this is the Wien bridge. The resistor and the capacitor are connected in a parallel, and here it's a series, here resistor R2 and R4. So by using the null deflection, means whenever the current is zero, means we are going to change the supply in such a manner, so therefore we are going to get current here is 0 ampere. So by using this 0 ampere null deflection method and the balanced condition, we are going to figure out the frequency, the unknown frequency. So by using the null deflection principle, if you are going to solve, finally we are going to get frequency of the unknown source is nothing but 1 by 2 pi into root over R1 C1 R3 C3. These are the R1 C1 and R3 C3. So based on these variables, we are going to get the frequency. So therefore, the Wien's bridge is used for the measurement of the frequency. And some other applications of the Wien bridge is also used for the capacitance measurements, and it is also used in the harmonic distortion analyzer, and it is also used in the high frequency oscillator. So therefore, the Wien's bridge is used for the measurement of the capacitance also it is going to measure, and also the harmonic distortion analyzer. It is also used in the harmonic distortion analyzer, and it also used in the high frequency oscillator. So therefore in the question, which bridge is used in the harmonic distortion analyzer, means it's a Wien's bridge. So here the inductance is measured by the ohm. The shortcut to remember ohm means H means Hayes bridge, O means Owens bridge, and M means Maxwell inductance bridge, A means Anderson's bridge, and M means Maxwell inductance capacitance bridge. So therefore by using this 5 bridge, we are going to figure out the inductance of the coil. For the capacitance, the shortcut is SD. SD means Shaker Dhawan. S means Shaker Dhawan. S is nothing but shearing bridge, and D is de-Sautis bridge. So by using these two bridges, we are going to figure out the capacitance and the frequency. Frequency is nothing but Wien's bridge, because W is equal to 2 pi F. So therefore it is very easy to remember. Frequency means Wien's bridge. So by using the inductance cancel of a given circuit can be measured by these 5 bridges, which are Ohm. Shortcut to remember: Hayes bridge, Owens bridge, Maxwell inductance bridge, Anderson's bridge, and Maxwell inductance capacitance bridge. For the capacitance, we are going to measure by the shearing bridge and the de-Sautis bridge, and for the frequency, we are going to measure by the Wien's bridge. So now we are going to solve the first second question. See the question here: which of the following statements is incorrect with respect to the potentiometers? So in the potentiometers, what is the incorrect statement of the 4 options? Option A, they can be used for the AC magnetic testing. Option B, they are basically null type instruments. Standardization of DC potentiometers is done by using DC potentiometers, and standardization of AC potentiometers is done by using AC sensors. So out of the 4 options, 1, A, B, C are the correct one, and option D is incorrect, but the correct option is standardization of AC potentiometers is done by using DC standard sources, but not by the AC standard sources. So therefore option D can be written as the correct option is here. D is the incorrect statement, but the actual statement is standardization of AC potentiometers is done by using DC standard sources. So let's discuss something more facts of this one. So now we are going to discuss about the potentiometer. The circuit in this question, the circuit in this figure is nothing but a DC potentiometer. Here the source is a DC one. That's what is called DC potentiometer. So this is a resistor. The resistor, which is a scale, means there is a scale on this resistor. So therefore this total uniform resistance means as the length increases, the resistance is also increases. So here there is some source. So suppose the source name is VA. So because of this source, we are going to standardize this scale, and is a VB is the unknown source. So with the help of this circuit, we are going to figure out the unknown voltage, because here the EMF is directly proportional to the length, which is scale on this resistor. So therefore, with the help of this one, we are going to figure out the unknown resistance also. So by the help of this voltage, we are going to standardize this potentiometer. Suppose if you are using the AC potentiometer, AC potentiometer is somewhat very complex circuit, but the basic principle is here we are going to use the AC source, but still here we are going to use the DC source in order to standardize this resistor with scale. So therefore here so potentiometer is basically used for the AC magnetic testing, and it is works on the principle of the null type. It's a null type instrument, means on the base of null deflection this instrument is going to work. So basically it is called as a null type instrument, means the current in the ammeter has to be zero at the condition, means balanced condition. So therefore here DC potentiometer is going to use the DC sources and the AC for the standardization, and the AC potentiometer is also going to use the DC sources for the standardization. So it's a very important thing to note here. So standardization is nothing but standardization is done in order to make the instrument more accurate and direct reading. Means basically the standardization is nothing but here we are going to use a small DC source in order to standardize this resistor. Means each and every scale is going to have a uniform of voltage division. So the EMF across the scale is directly proportional to the length of the scale. So by this we are going to figure out the unknown voltage also. So now we are going to solve the 43rd question. See the question here. A lead compensator GC of S is equal to 1 plus 0.12 S by 1 plus 0.04 S can provide a maximum shift of. So here it is a lead compensator. Now we need to find what is the maximum phase shift provided by this compensator. Option A 90 degree, option B 60 degree, option C 45 degree, option D 30 degree. So out of the four options, option D 30 degrees is the correct solution of this question. So let's discuss something more facts of this one. In the question they are given the lead compensator transfer function, which is 1 plus 0.12 S by 1 plus 0.04 S. So now we need to check whether it is a lead compensator or not. So the zero is nothing but minus 1 by 0.12 and the pole is minus 1 by 0.04. So therefore here that 0 is nearer to the origin. So therefore we can say that as 0 is near to the origin, this is said to be a lead compensator. Lead compensator means the output is going to lead the input. Means the lead compensator means the output is going to lead the input. So here in the question, so the basic standard lead compensator here, the transfer function is k into 1 plus ts by 1 plus alpha ts. So if you compare these both equations, t is nothing but 0.12 and alpha t is equal to 0.04. So here now alpha is equal to t, I am going to keep it down, so therefore 0.04 by t. So t is nothing but 0.12. So therefore if you do the calculation, we are going to get alpha is equal to 3. So at the maximum phase shift, this is a triangle. So if you remember this triangle, we can easily solve the numerical. So this is actually based in the theory only, but for the problem numerical, if you remember this one, we can easily solve the question. So this is phi m, the maximum phase shift angle. This is 1 minus alpha, the base is 2 root alpha, and the hypotenuse is 1 plus alpha. So therefore the sin phi m is equal to opposite by hypotenuse, which is 1 minus alpha by 1 plus alpha. So we know the alpha is equal to 1 by 3. So 1 minus 1 by 3 by 1 plus 1 by 3. If you solve this one, we are going to get 1 by 2. So therefore the sin phi m is equal to 1 by 2. So phi m is equal to 30 degrees. So therefore maximum phase shift in the output is 30 degrees. Suppose if the input to this compensator is Vm sin omega t, means output, the output which is obtained by this circuit is Vm sin omega t plus 30. This is the maximum shift. Not more than this, it cannot be possible. Means the phase shift can be less than 30, but not more than 30. Means 30 is the maximum phase shift which is provided by this phase led compensator. So now we are going to solve the 44th question. See the question here. The open loop transfer function of a system is g of s h of s is equal to 16 into s plus 1 by s into s plus 2 into s plus 4. So the centroid and the angle of asymptotes are. So now we need to find what is the centroid and the angle of asymptotes for this open loop transfer function. So out of the four options, option C, which is the centroid is minus 2.5 and the angle of asymptotes are 90 degree and the 270 degree. So let's solve this numerical. So the open loop transfer function is g of s of s is equal to 16 into s plus 1 by s into s plus 2 s plus 4. This is given in the question. So now we need to find what is the poles of this one. Poles is nothing but the denominator part roots. So therefore the denominator part roots are s is equal to 0, s is equal to minus 2 and s is equal to minus 4 are the denominator roots. The number of roots are nothing but 3 because 1, 2, 3 means 3 roots. So now we need to find number of zeros. Zeros is nothing but the numerator part is equal to 0. If you do equal to 0, what are the roots? What we got in the numerator is called as a 0. So therefore it is minus 1. So there is only one root. So therefore now the centroid is nothing but summation of real parts of pole minus summation of real parts of 0 by number of poles minus number of zeros. So here the roots, the real part roots we need to add for the poles. So therefore we need to add 0, minus 2, minus 4. We have added minus, minus. So now we need to find the summation of the real parts of zeros. So there is only one 0 with minus 1. So therefore minus 1 by number of poles are 3 and the number of zeros are 1. So therefore 3 minus 1. So if you solve this one, we are going to get here the centroid is minus 2.5. So the centroid is minus 2.5. So the number of asymptotes is nothing but mod of p minus z. Means number of poles minus number of z, means the number of asymptotes is going to tell you that number, that many branches are going to go to the infinity. So therefore here mod of 3 minus 1 is nothing but 2. So therefore 2 branches are going to the infinity. So theta, what is the angle? These asymptotes, what is the angle they are going to make with the positive x-axis? Is nothing but 2q plus 1 into 180 degree by number of poles minus number of zeros. So we know p minus z is equal to 2. So therefore 2q plus 1 into 180 by 2. So therefore here, suppose if q is equal to 0, we are going to get a theta is equal to 90 degree. And if q is equal to 1, we are going to get the theta is equal to 270 degree. So therefore, the two branches, one branch is going to do the 90 degree and another branch is going to infinity at 270 degree. So now I am going to draw the root locus diagram. So now I have made the points of poles, which is 0, minus 2, minus 4 and the 0 is minus 1. So therefore, here, if you stand here, there is only one root. There is only one root which is present at the right side. So therefore it is an odd number. So therefore this is in the root locus. So if you stand here, there are two roots. So therefore roots to the right side of you. So therefore it is not a root locus. So therefore if you stand here, then there are three roots which are right side of you. So therefore as there are three roots is odd number. So therefore this is in the root locus. So therefore this is also root locus. This branch is also, this region is in the root locus and this region is also in the root locus. But if you stand here, there are four roots. Four roots is nothing but even numbers. So therefore this is not in a root locus. So therefore only these two regions are in the root locus. So therefore this zero root is going to terminate to the pole is going to terminate at the 0, minus 1, and also these two roots, the centroid is nothing but here minus 2.5. So therefore at the centroid minus 2.5 we are going to draw the straight line. This is at 90 degree and this is minus 270 degree. So therefore these root locus are going to come and intersect each other and they are going to go to the infinity. So therefore this is a root locus diagram. So this 0, the pole 0 is going to terminate at the minus 1, 0, and the remaining two poles are going to go to the infinity along the direction of 90 degree and also the 270 degree. So now we are going to solve the 45th question. See the question here. If a synchronous motor is running at a leading power factor, its excitation induced voltage EF is. So here, when a synchronous motor is running at leading power factor, what is the excitation induced EMF voltage? The options are equal to the terminal voltage VT, higher than the terminal voltage VT, lesser than the terminal voltage VT, dependent upon supply voltage VT. So what are the four options? Option B, D higher than the terminal voltage VT. So let's solve this numerical. So now I have drawn a synchronous meter. The diagram is the supply voltage is VT and the induced EMF voltage is EF, and the current in the synchronous motor is IA, and this is the synchronous resistance and the synchronous reactance. So therefore here what I am going to do is phi is nothing but a power factor angle. It is the angle between the EF and the IA. The angle between the induced voltage EF and the current IA is said to be the power factor angle. In the question they have given the phi is nothing but leading angle they have given, means the current IA is going to lead the voltage EF. So the basic voltage equation is nothing but by KVL we are going to get here VT is equal to EF plus IA into RS plus JXS. So as RS is a very small value, now I am going to neglect this one. So therefore finally I am going to get here IA into JXS because RS is very nearly equal to 0. So therefore this is IA into JXS. So therefore now I am going to draw the vector diagram. See, let me assume the VF is the base. So this is a VF, EF is the base. So therefore in the question they are given phi is the leading power factor, means the current is going to lead the EF, means the current is going to lead. So therefore this is the IA. So this is the IA and this is the angle phi because current is going to lead. So now I need to draw IA into JXS. So JXS is nothing but 90 degree phase shift with respect to IA. So therefore this is a 90 degree, means the angle between these both is nothing but 90 degree. So therefore this is the angle, this is a vector is nothing but IA into XS. So this is the length of this vector Ia into xs. So now Vt is nothing but Ef plus Ia into xs. So therefore this is called as the Vt. This is called as a Vt. So if you see carefully, the length of Ef is greater than the length of Vt, because this is the length of Vt and this the length is Ef. This vector has length of Ef and this length as a vector of this vector has length of Vt. So therefore this Ef is greater than the Vt. If you see clearly also, so therefore Ef is nothing but the length of the vector is very greater than the length of Vt. So this is the question they have asked. So therefore the induced voltage is very greater than the terminal voltage or the supply voltage in the leading power factor region. So a small note here, whenever the phi is leading, Ef is always greater than the Vt. But at the phi is called UPF and the lagging power factor, always the Vt will be greater than the Ef. So at UPF and lagging, Vt is greater than Vf. But at phi is equal to leading, only Ef is always greater than the Vt. So this is also very important point. So now we are going to solve the 46th question. See the question here. In a group of 6 women, there are 4 dancers, 4 vocal musicians, 1 actor and 3 violinists. Girija and Vanaja are among the violinists. Jalaja and Shailaja do not know how to play on the violin. And Shailaja and Tanuja are among the dancers. Jalaja, Vanaja, Shailaja and Tanuja are the local musicians. And 2 of them are also violinists. If Pooja is an actor, who among the following is certainly a dancer and a violinist? So here the options are Jalaja, Pooja, Shailaja, Tanuja. Out of the 4 options, option D, Tanuja is the correct solution of this question. So let's solve this numerical. So in the question they have says that in a group of 6 women, there are 6 women. The 6 women names are Girija, Vanaja, Tanuja, Jalaja, Shailaja and Pooja. These are the 6 girls' names. So here they have given there are 4 dancers, 4 vocal musicians and 1 actor and 3 violinists. Girija and Vanaja are among the violinists. Girija and the Vanaja are among the violinists. So therefore these both are the violinists. While Jalaja and Shailaja do not know how to play on the violin. So therefore these 2 girls don't know how to play the violinists. So therefore these 2 are the not violinists. Means Jalaja, Shailaja are not the violinists. Shailaja and Tanuja are among the dancers. So these 2 girls are the dancers. Shailaja and the Tanuja are the dancers. Jalaja, Vanaja, Shailaja and Tanuja are all vocal musicians. So Jalaja, Vanaja, Shailaja and Tanuja, all these 4 girls are the vocal musicians. And 2 of them are also violinists. So among these 4, 2 people are the violinists. So therefore if you see carefully, Jalaja is not a violinist. So therefore this girl is not a violinist. And Vanaja is also a violinist. So therefore this girl is a violinist. And but Shailaja is not a violinist. It's already given. So therefore she is not a violinist. But in the question they are given among these 4, the 2 are the violinists. So therefore this Tanuja is also a violinist. So therefore now this Tanuja is also a violinist, because there are 3 violinists. Only 2 we know. So the remaining girl is a Tanuja. Therefore Tanuja is also a violinist. If Pooja is an actor, so Pooja is an actor. So now Pooja is an actor. Who among the following is certainly a dancer and a violinist? So now you need to see the dancers and the violinists, which name is common. So here if you see carefully, here Shailaja is a dancer but not a violinist. But if you see Tanuja is a dancer and also a violinist. So therefore Tanuja is the girl, is a dancer and a violinist. So now we are going to solve the 47th question. See the question here. At a particular unbalanced node, the real power specified are leaving the node, which is 20 megawatt and the 25 megawatt are the real powers which are going to leave the node, and the entering the node is 60 megawatt and the 30 megawatt. So therefore the 60 megawatt and 30 megawatt are going to enter the node. So the balance power will be, so option A 30 megawatt leaving the node, option B 45 megawatt leaving the node, option C 45 megawatt entering the node, option D 22.5 megawatt entering the node and 22.5 megawatt leaving the node. So out of the 4 options, option B 45 megawatt is the leaving the node is the correct solution of this question. So let's solve this numerical. So here this is a particular node. At this node the powers which are going to leave this node are 20 megawatt and the 25 megawatt. So in this branch the power which is leaving is 20 megawatt, and another branch in this the power is leaving this node is 25 megawatt. So here at the same node, the entering powers are 60 megawatt and the 30 megawatt. So therefore here there is a 60 megawatt of power which is entering the node, and through the another branch the power is 30 megawatt of power which is entering the node. So the balance is, suppose let me assume the other branch, the lagging branch has a power of x. So therefore by balanced, because the power is always conserved, means the input power is always equal to the output power. So therefore here the entering the powers are 60 megawatt, so entering is equal to leaving. So because the power is always conserved, so therefore entering is equal to leaving. So I have assumed in the other branch the real power is leaving the branch. So therefore here the entering is 60 and here also is entering is the 30, and here leaving is, so x 25 plus x plus 25 plus 20, all these powers are leaving. So therefore 60 plus 30 is equal to 90 is equal to x plus 25 plus 20 is nothing but 45. So therefore x is equal to 90 minus 45 is equal to 45 megawatt. So we got here positive sign, means our direction is assumed is correct. So if it is negative, means our assumed direction is wrong, but here we got x is equal to plus 45, means our assumed direction is also correct. So therefore here 45 megawatt of power, the real power is going to leave the node. So therefore option B is the correct solution, means 45 megawatt of power is going to leave this junction, means always the power is conserved, means input power is equal to output power in a branch. So now we are going to solve the 40th question. See the question here. A three-phase transmission line operating at supply voltage Vs is equal to 400 kV and has ABCD parameters of A is equal to D is equal to 0.8 at an angle 0, B is equal to 100 at an angle 90 ohms, and C is equal to 0.5 into 10 to the power of minus 6 at an angle 90 mhos. What is the value of the inductive shunt reactor required for compensating Ferranti effect? So there are four options. Option A 1500 ohm, option B 750 ohm, option C 500 ohm, option D 300 ohm. So out of the four options, option C 500 ohm is the correct solution of this question. So let's solve this numerical. So in the question they are given the supply voltage is nothing but 400 kV and the parameters, ABCD parameters also they are given. A is equal to D is equal to 0.8 at an angle 0 degree, and the B is equal to 100 at an angle 90 degree, and C is equal to 0.5 10 to the power of minus 6 at an angle of 90 degree. So now we need to find what is the reactance we need to kept at the load end. So therefore we are going to compensate the Ferranti effect, means the Ferranti effect is nothing but at the no load conditions, for the medium and the long transmission lines, the receiving end voltage will be greater than the supply voltage. The important point is you need to remember only for the medium transmission lines and the long transmission lines at the no load condition, the receiving end voltage will be greater than the supply end voltage, but not for the small transmission line. For the small transmission line at no load condition, always the receiving end voltage is equal to supply end voltage, because there is no capacitance effect. For the small transmission line there is no capacitance effect, but for the medium and the long transmission line there is a capacitance effect. So because of these reasons the receiving end voltage will be greater than the supply end voltage at the no load. So therefore now we need to keep a reactor at the receiving end voltage. So therefore we are going to compensate the Ferranti effect, means we are going to make the receiving end voltage is equal to supply end voltage. So therefore this is the basic two-port equation in terms of the ABCD parameters. Vs, Is, supply voltage, supply current, and the receiving voltage, receiving current, A, B, C, D. So now I am going to write the first equation. Vs is equal to A into Vr plus B into IR. So Vs is equal to A into Vr plus B into IR. So now by keeping this shunt reactor, I am going to make the receiving end voltage is equal to supply voltage. So therefore the supply end voltage is now became the receiving end voltage. So therefore in place of Vs, I am going to make it as a Vr. So therefore Vr is equal to A into Vr plus B into IR. So now I am going to take this Vr to the left forward. So therefore Vr comments. So 1 minus A is equal to B into IR. So therefore Vr by IR is equal to B by 1 minus A. So Vr by IR is nothing but voltage by current is nothing but the reactance or the impedance of this circuit is nothing but, you can write here Z or you can write here X. No need, nothing to worry. So therefore Z is equal to B minus A. We know the value of B is nothing but 100 angle 90 degree and A is equal to 0.8. So therefore 100 angle 90 degree by 1 minus 0.8 at an angle of 0. So if you do this one, we are going to get here the impedance which we need to connect, across the inductor, across the receiving end is nothing but 500 at an angle 90 degree is nothing but 500 J, means we need to keep a inductor, of magnitude value 500 ohms. this much amount of inductor we need to keep. So therefore the receiving end voltage will be equal to the sending end voltage at the no load condition. So therefore, see, I have already told you, for the small transmission line there will be no capacitance effect. So for the small transmission line there will be no charging capacitance. So because of that reason, always at no load receiving end voltage is equal to supply voltage, but at medium and long transmission line there will be charging capacitance effect. Because of this charging capacitance only, the receiving end voltage will be always greater than supply voltage at the no load condition. And this is a very important question always asked in the PSU examinations. So for the medium and the long transmission lines, the Faraday effect is going to occur, but not for the small transmission line. This is a very important point. So now we are going to solve the 49th question. See the question here. The geometric mean radius of a connector in terms of the radius r of an individual strand for 3 equal strands are shown in figure is. So for these 3 equal strands we have to find what is the geometrical mean radius of the conductor. So out of the 4 options, option A, which is option A, is the correct solution of this question. So let's solve this numerical. So these are the 3 connectors. For these 3 connectors we need to find what is the geometrical mean radius or the self GMD of this connector. So therefore, because of these 3 connectors we are going to get the net connector. So each radius is nothing but r. So now what I am going to do is, here each circle has a radius of r. So distance between these 2 points is nothing but r plus r, 2r. And here also the distance between these 2 points is 2r. Here also the distance between these 2 points is 2r. So therefore now let me assume this is a connector 1, connector 2, connector 3. So therefore now how to write the geometrical mean radius? So therefore the geometrical mean radius is nothing but our self GMD. Always here we need to write here, suppose I am going to take the first connector. So from the first connector self GMD. The first connector self GMD is nothing but it's e to the power of minus 1 by 4 into r. This is the self, or 0.7788 into r. This is the self GMD of the first connector. Now the distance between the first connector and the second connector. So center to center distance is 2r. You have to do the multiplication. Now from 1 to 3rd. So 1 to 2 is over. Now 1 to 3rd. The distance between the 1 to 3 is again 2r. So therefore 2r. So this is for the first connector. Now for the second connector, same fashion again here. Now the self GMD of the second circuit is, the second connector is nothing but again 0 e to the power of minus 1 by 4 into r. Again from 2 to 1, what is the distance between the 2 to 1? This is 2r. And similarly 2 to 3, the distance is 2r. Similarly for the third connector, same thing here. For the third connector, the self GMD of the third connector is nothing but again e to the power of minus 1 by 4 into r. Again 3 to 1 is again 2r. Again here 3 to 2 is again 2r. So now this is the way you need to write for GMD. Again whole bracket, again whole bracket. Here the number of connectors are 3. So therefore here we need to take here 1 by 3 square. You need to do always the, so there are 3 connectors, right? So 1, 2, 3. So 3 connectors you have to take, and you always have to do the square here. So therefore this is the procedure. So simplify, if you simplify this one, so each term is same, identical. So therefore simply I can write e to the power of minus 4 into 2 to the 4r cube whole to the power of 3 whole to the power of, this is 1 by 3 square. So 3 into 3. So 3 get cancelled. So finally cube root of e to the power of minus 1 by 4 into 4r cube, or you can write it in this manner also. Cube root of e to the power of minus 1 by 4 into r into 2r into 2r. This is also way you can write. So finally this is the solution of this question. So always for each and every connector you need to write this bracket, and then you have to take 1 by number of strands in a connector is 3. So therefore always you have to do the square of that one. So this is the procedure. So finally this is the solution of this question. So now we are going to solve the last question of this lecture, 50th question. See the question here. An 8-pole DC generator has a simplex wave-wound armature containing 32 coils of 6 turns each. If flux per pole is 0.06 Weber, the machine is running at 250 RPM, the induced armature voltage is. So what are the 4 options? Option C, 384 is the correct solution of this question. So let's solve this numerical. This is a DC generator. In the question they are given the number of poles is 8 and the parallel paths. The number of parallel paths is nothing but it's a wave wound. Wave wound means the number of parallel paths will be 2. And also they are given the coils is nothing but 32 and the turns is 6. So we need to find what is the number of total conductors. So total conductance is nothing but coils into turns into 2. Means if you do the multiplication of coils into turns, we are going to get the number of turns. But for each turn there are 2 conductors. So therefore now we need to find the total number of conductors. So therefore always we need to do the multiplication of 2. I am repeating again. See, if you multiply the number of coils and turns, we are going to get the total number of turns. But for each turn there are 2 conductors. So if you need to find the total conductors, so therefore we need to multiply by 2. So therefore here 32 coils into 6 turns into 2. So we are going to get here 384 conductors. So here always they are given the flux per, means each pole is going to give a flux of 0.06 Weber. So and the speed of the rotor is nothing but 250 rpm. So we need to find what is the generated voltage EMF which is generated. Eg is equal to P5 into N by 60 into Z by I. This is a very basic equation. We know the value of P, which is 8, and the phi is 0.06, N is 250 by 60 into Z. It is nothing but 384 by 2. So if you solve this, all these things, we are going to get finally Eg is equal to 384 volts. Means this much amount of voltage is going to be generated by this generator at all these conditions. So by this lecture, we have successfully completed the 50 questions which are asked in the AP Transcript 2019 W solutions. If you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button. So whenever we upload a new video, the direct notifications comes to mobile. If any improvements in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care, and bye bye.